this is Miss Wu, and in our last lesson we have done the optimization problems, how to use first derivative to find the local minimum maximum or global minimum maximum. We also call them absolute minimum or maximum. And in this lesson we are going to continue work on the minimum or maximum from real-world applications, and before that we want to see in our last lesson we have done is we find the first derivative equals 0 where you may have the maximum and the minimum. So in this lesson we are going to introduce the first derivative test. What first derivative test means, if we have the xy axis and at certain point f prime equals 0 for the graph. So on the left, if we have the graph is increasing, so it means the slope is positive, f prime is positive, and on the right side of the f prime equals 0 is decreasing, so the slope is negative. Then we are going to see if the f prime is changing the sign from positive to 0 then to negative. Then at f prime equals 0 you have a local or maybe absolute maximum, but for sure we have the local maximum. So when the first derivative changes the sign from positive to negative, so increasing to decreasing, then at f prime equals 0 you have the local maximum. And we are going to continue to see, so if this is f prime equals 0 point, and on the left side if the graph is decreasing, so the f prime is negative, then here is 0, on the right side is increasing, is positive. At f prime equals 0 we know that you will have a local minimum. Okay, so you will see when the first derivative changes sign, then you may have local minimum or local maximum. So now we are going to see another example that at this point we have f prime equals 0, and on the left the graph is decreasing, so it's negative, the slope f prime is negative, and on the right side is decreasing again. So at this point you may have the derivative, the slope is 0, but you don't have a local minimum or maximum. So if the derivative doesn't change the sign at f prime equals 0, the left side, right side doesn't change the sign, then you don't have local minimum or maximum. So we are going to continue to see at this point f prime equals 0, and if on the left side the graph is increasing and on the right side is increasing, so both f prime is positive, and at this point the f prime is 0, but you don't have any maximum or minimum. So this is one way that you could check to see if you have a maximum or minimum value at that f prime equals 0. Okay, this we call first derivative test. So now we are going to look at one example and see how we can use the first derivative to find the maximum or minimum in financial field. So maximum revenue for an outdoor concert, a ticket price of $30. You have seen this type of question in grade 10 grade 11. Then we are going to, at that time, we use the vertex form. Find the vertex to find the maximum, minimum, and this time we are going to use first derivative to find the maximum or minimum. So $30 and attracts 5,000 pupils for each $1 increase in the ticket price. 100 fewer people will attend. So the revenue is a product of the number of people attending and the times the price per ticket. So we are going to introduce a variable let x represents the number of $1 increase, and the final equation expressing the total revenue in terms of x. So for such question, I want you to draw a chart, but you don't have to, okay? So question A, x is a $1 increase, so we know that the revenue is the ticket price times number of people attend. Then this is a revenue. Revenue equals these two times. So original price is $30. So number of people is 5,000. So the revenue is just $30 times 5,000. Then X dollar increase. So 30 plus each time you increase $1, you increase X times. So if we increase $1, then it will be 5,000 minus 100 pupil. Now increase X times. So X times $1. Then it will decrease 100 times X. So these two times together give you the revenue. So this is how you get the equation. So revenue equals ticket price is 30 plus X dollars. Then the pupil attending will be 5,000 minus 100 X. So this is the equation of total revenue in terms of X. Then state any restrictions on X. Can X be negative number? I think it will be, because it's just you reduce the price. So if X negative, it will reduce the price. So we don't want ticket price to be negative, so X need to be the minimum for X will be decrease 30 times, and you have $0. So need to be greater than negative 30 for the X increase. And for this part, we don't want the number of people to be negative, so we solve it. We have X equals 50. So you don't want to increase more than $50, because when you increase more than $50, you have negative people attend. So the maximum will be for the X times increase will be 50 times increase $1. So this is a negative 30 less than X, then less than 50. Okay. These two are the extreme situation. So when X equals negative 30, the ticket price is 0, so you have the revenue equals 0. And when X equals the maximum number 50, you sub in, number of people will be 0, so the revenue will be 0. So these are the two ending points. From the restrictions, this is a domain. From the domain, you are able to find the endpoints. Then from the endpoints, we can find the maximum. We can find the revenue value. Then after we have the maximum or minimum value we have found, we are going to compare them with this end value. Okay, so question C, it asks you to find the ticket price that gives maximum revenue. So we want to find the derivative dr over dx equals 0. So this one is two factors times together, so we use a product rule. So uv then derivative equals u prime v plus uv prime. Okay, u is 30 plus x. This derivative give you 1. Then 5,000 minus 100x plus first bracket, we keep it there and we just the derivative of the second bracket. So constant is 0, derivative of negative 100x, 1 bring to the front, then 1 minus 1, x to the exponent 0 is 1, so we have minus 100. Then we simplify and solve, let it equal 0 and solve it. So we have 5,000 minus 100x plus this times give you minus 3,000 minus 100x. We have 2,000 minus 200x. So in order to find the maximum minimum, we want to let the first derivative equal 0. So let dr dx over dx equals 0. So we have 2,000 minus 200x equals 0. This is a linear equation. We could move the 200x to negative 200x, move to other side is opposite operation is plus. So 2,000 equals 200x, move the 200 to this side is opposite operation is division, so x equals 10. Then we are going to sub this x equals 10 to this r to find out what's the r value. And also here we could use this x equals 10, use our first derivative test to find out. This is x equals 10, r prime equals 0. So on the left side of this x equals 10, we could just pick any point. For example, x equals 1, sub into the dr over dx. Then we put 1 here, you will find out 2,000 minus 200 is positive. So we have positive slope this side. And this is equal 0. Then on the right side, we could just pick any numbers. We could just pick a big number. 100. We put 100 here. 2,000 minus 20,000. We know it's negative. Negative means the slope is negative. So from here, we are able to say you have a local maximum here. Now we sub in the x equals 10 to the original revenue equation. Okay, so we have r equals 30 plus 10. This is our ticket price. Then times 5,000 minus 100 times 10. Then we have 40 is our ticket price. This is 4,000 is pupil attended. attending, so we have $160,000 revenue. And compare it with our endpoint, you will find out that this is our maximum value. So this is a maximum value. Then we are going to see question D. Will your answer to part C change if the concert area holds a maximum of 1,200 people instead of this 5,000? They change it to 1,200 people. Then we are going to see if we couldn't have 4,000 people, then what will happen? So we are going to see now is 1,200 people only. So 5,000 take away 100x. So we move it to other side is negative 3,800 equals negative 100x. Then bring the negative 100 to other side, we have x equals 38. So this time it means we are going to see set that one as our endpoint. Then we are going to see the revenue. It will be and this x value becomes a restriction to the domain. You cannot have x less than this number. If x less than 38, 5,000 minus 100 times that number will give you the number of people attending greater than 1,200. So x need to be greater than 38 but less than 50. So we sub in x equals 38. Then to find the revenue, we are going to have 30 plus 38. Then 38 sub in is 1,200. So you will have 81,200. And this compared to the maximum revenue, you will see the maximum revenue is still as before. So the maximum revenue doesn't change. So the maximum revenue is $160,000. So the endpoint didn't change the maximum revenue. So this is a left side positive, right side is negative. For the first derivative, you have a local maximum. And the endpoint we checked, they are not greater than the local maximum. So you have an absolute maximum. So this is for the example 1. And after that, we are going to see the example 2. So example 2 is involving finance again. So minimum cost. A cylinder chemical storage tank with a capacity of 1,000 meter cubed is going to be constructed in a warehouse that is 12 meter by 15 meter and a height of 11 meters. So it's kind of like a warehouse is a rectangle prism. So this is a 15 meter long, 12 meter wide, and 11 meter high. So they want to build a chemical storage tank in this warehouse. The specifications call for the base to be made of sheet steel, and that cost $100 per meter squared. The top to be made of sheet steel, but it's different quality, so costs $50 per meter squared. The wall to be made of sheet steel, that cost $80 per meter squared. So it asks you to determine whether it is possible for a tank of this capacity to fit in the warehouse. If it's possible, state the restrictions on the radius. And if fitting the tank in the warehouse is possible, determine the proportions that meet the conditions and also minimize the cost of the steel. So we are going to see, we put a cylinder in the warehouse. We put a cylinder in the warehouse. The height is h and r is the radius. So the volume need to be 1000 meter cubed. So we are going to see question A. The volume is pi r squared times h for this cylinder, and the height equals V over pi r squared. So the maximum height will be less than 11 meter. And from here we are able to find out $1,000 divided by pi r squared equals 11. Then we want to find the r. We move the r squared to other side. We have 1000 divided by pi times 11 equals r squared. So r equals square root 1000 divided by pi times 11. Do the calculation, we are going to be able to find out the, so height is maximum, then this one is our minimum. And from the warehouse is 12 meter wide, so the r is not able to greater than 6. If greater than 6, then the cylinder will go outside of the warehouse. So R max will be half of the width of the warehouse. So we have R greater than square root 1000 divided by 11 pi, but less than 6. So this is the domain for R. Then after that, we are going to see the cost. And in the cost, so it asks you to minimize the cost. So it means like y equals whatever the maximum or minimum quantity. So y represent the cost. So we are going to write y equals, the reason why we want to write h equals, because in the cost equation, we want to keep only one input. So we want to change everything to H or everything to R. So the $100 for the base. The base is just a circle, so it's 100 times pi r squared. This is our base. Then plus 50 for the top. So 50 times the top is pi r squared. Then plus $80 times the area for the wall. The wall is the circumference of the circle times h. So 2 pi r, then h. So this is our cost. And in this equation, the right side, we have two variables. We don't want to see two variables, so we want to replace the h with r. So we have 100. You could change everything pi r squared to h. It's up to you. So pi r squared plus 50 pi r squared plus 160 pi r. Then h is V, volume is 1000 pi r squared. So you will see now you have only r as the input variable. So we combine the like terms, 150 pi r squared. This one pi r cancel out. We have 160,000 over r. In order to find the minimum or maximum, we want to find the derivative. So we are going to find dy over dr equals. So this one, 150 pi is constant. So times 2, then degree minus 1 is r1 plus 160,000. This one we can think is r to the exponent -1. So -1, then r minus 1 give us -2. So we want to let the derivative equal 0 and solve for r. We have 300 pi r minus 160,000 r -2 is r squared equals 0. We don't want to see the denominator, so we want to change times each term by r squared. Then r squared cancel out. We will have the no denominator. So we have only one term with r, so we can isolate it by moving the numbers to other side. So 300 pi r cubed equals 160,000. Then move the 300 pi to other side. We have r cubed equals 1, cancel 2 zeros, so 1,603 pi. Then we solve for r, we move the exponent to other side, it will be third root. Then do the calculation, r is approximately 5.5. So we sub in the endpoint and also these two values to check which one give you the minimum. And from here we also could check if you have the minimum here. So this is R approximately 5.5. So if we draw so this is a 5.5 at this point, dy over dr equals 0. Then we could pick just r equals 1. Then we sub in the 1 here. We are going to have 300 pi 1 minus 160,000 divided by 1. So this number is greater than that, is negative. So it will be this direction. And after that we could pick another number. For example, is 100. So we put 100 here. You will find out this one times 100 is greater than this one divided by 100 squared. So it will becomes positive. So this side is positive. So from the first derivative test, we are going to see here we have a local minimum. Then we need to find the endpoint. So we have the endpoint R equals square root 1000 divided by 11 pi, and also we have the endpoint R equals 6. We sub in each of them to the original equation for y. So we have sub in y equals approximately we have 43,345.89 cents. And we sub in this one to y. We do this calculation. We have $43,379.81. R equals 6. We have y approximately $43,631.37. And from here you will see this is the minimum. First number same, second number same, third number same, and this one is smaller. So then we know that when R equals 5.5, we have the minimum cost. So therefore, when R equals 5.5, then we solve for H. H equals 1000 divided by pi R squared. So 1000 divided by pi R squared is approximately 10.5. The minimum cost is $43,345.89. So this is all for today's lesson, and from today's lesson we have that is from the first derivative equals 0 to find the possible maximum minimum point, and from the first derivative test, if first derivative is changing the sign from negative to positive, you have the local minimum. If from positive to negative, we have the local maximum. And also you have to compare the endpoints, and from the derivative equals 0 point and also the endpoint to check which y value give you the maximum minimum. Maximum minimum, the quantity we introduce that variable as y. Thanks for watching.